Let's take your attendance. Okay. So let's continue where we left yesterday. So we are just halfway of discussing thermodynamics. Okay. So how thermal affects the movement of the fluids. Okay. So today what we're going to learn is something new. I don't know whether you learned this before or not. Okay. You heard about? Yeah. Okay, so yeah, so this is what we're going to learn today. Maybe in your early studies, maybe your teacher might tell this something called internal energy. Okay, so every substance has its own internal energy. So you can see the chair, the atoms, looks like the chair doesn't move, but the atom inside is actually vibrating, right? So it's moving. So because it's moving, what type of energy it possesses? It moves. So it has a kinetic energy it possesses, and also it has potential energy. Okay, it has potential energy. Why it has potential energy? Because it's bonded to the intermolecular force. Okay, because if anything has an intermolecular force, that means it possesses some potential energy. Okay, like you have gravitational potential energy. Why? Because there is a force pulling you down, attractive force. And if you don't have that force, you don't have potential energy, gravitational potential energy. Okay, so what is internal energy of a substance? Okay, who possesses greatest internal energy? Solid, liquid, or gas? So which has the greatest internal energy? First of all, what is meant by internal energy? So that's the definition written there. So internal energy of a system is the sum of kinetic energy and potential energy possessed by the atoms due to random motion. Okay, or due to moving randomly. Okay, the moving randomly like one month, must say randomly. Okay, so what is internal energy of a substance? Is the total kinetic and potential energy possessed by the particle due to random motion. Okay, kinetic plus potential. Okay, that's the internal energy. Okay, so symbol U equals to EK plus EP, but I think I forgot. Please put the summation sign. The sum of EK plus EP. The total EK plus EP. Okay, so solid, liquid, gas. Okay, which has the highest potential internal energy? Solid, liquid, or gas? Based on this definition. Solid, liquid, gas. Which has the greatest kinetic energy? Of course, gas. Everyone knows that. Gas has the greatest kinetic energy. Solid, liquid, gas. Which has the greatest potential energy? This could be maybe some of you make a mistake. Which has the greatest potential energy? Who will have great potential energy? The one with the strong intermolecular force has great potential energy, or the one very weak intermolecular force will have a great potential energy? Who said the one has a strong intermolecular force will have a greater potential energy? Strong intermolecular force means great potential energy. Many, yeah? Many saying is strong bonding means more potential energy, right? Okay, now let's see. Okay, you learn about gravity already. Okay, so tell me, now you possess a greater gravitational potential energy, or when you're moving away from the Earth's surface, go to the outer space, you gain more. You have more gravitational potential energy. When you have more gravitational potential energy, you're moving away, right? When you're far away from the Earth, you have the greatest gravitational potential energy. The intermolecular force is similar to your case. The Earth gravitational pull is like the intermolecular force between you and the Earth. You are a molecule, the Earth is another molecule, like large molecule. So tell me, when you gain greatest gravitational potential energy, when you have a strong intermolecular force, or the force is strong, or when the force is weak, when you have the greatest gravitational potential energy, and the force between you and the Earth become very weak. Okay, what is the highest gravitational potential energy you can attain? This is few weeks back, right? We do gravity. What is the highest gravitational potential energy you can attain? How much? Still remember? All focus to AS. Okay, 0. The maximum gravitational potential energy you can attain is 0. Where you can attain that? At infinite. Okay, when there is no attractive force by the Earth, you have 0 potential energy, gravitational potential energy. So highest potential energy you can attain is 0. Other than that, get closer, the potential energy become negative, because attractive force always yield a negative potential energy. Okay, now, based on the same idea, is for the substance too. For the substance also, same idea. The two atoms have a intermolecular force. Solid, liquid, gas. Which has the greatest attractive force? Of course, solid. Okay, so solid has the greatest potential energy or least potential energy? The least. The solid has the least potential energy. Okay, although the magnitude is big, but it's highly negative. Potential energy possessed by the atoms in solid are highly negative. Okay, the potential possessed by gas particle are less negative. Okay, we can say less negative. Analog to gravity. Analog to gravity. So what I can say, go to the whiteboard for a while. Explain this stuff. Okay. So solid, liquid, gas, kinetic energy. Of course, the highest is gas. Okay. Liquid is not that much. Solid has the lowest kinetic energy for sure. This is no problem. Okay. The potential energy, the highest is gas. Okay. The least is solid again. The liquid is intermediate. If I give a value, potential energy, maybe gas as maybe solid has a potential energy of negative 10,000 joule. It's negative. Okay. Liquid maybe have a potential energy of negative 5,000 joule. Gas will have a potential energy of maybe negative 5 joule. So negative 10,000, negative 5,000, negative 5, negative 5. So technically, which has the greatest potential energy is negative 5, close to 0. Okay, more negative we consider low, the potential energy. So gas got two types, right? What are the two gases you have? Real gas and the other one is what? Ideal gas, right? Hypothetical gas, ideal gas. Real gas will have some potential energy because they have intermolecular force. Weak. Ideal gas, no intermolecular force. So what is the potential energy possessed by ideal gas? How much? 0. Potential energy on ideal gas is 0. Okay. Yeah. So conclusion is, who has the greatest potential energy is gas. Okay. It has the highest kinetic energy. It possesses the highest potential energy. Therefore, gas has the greatest internal energy. Okay. What is meant by internal energy? The sum of kinetic and potential possessed by all the particles in the substance due to random motion. Yeah. So this internal energy is like a highlight important quantity you need to know for the following discussion. Okay, which all are new stuff. Okay, so majority of you raised up just now and you said stronger intermolecular force, greater potential energy. So stronger intermolecular force, the magnitude is great, but it's highly negative. So we consider low potential. Okay. Okay, now early studies, ideal gas. When kinetic energy rises, what you increase, kinetic energy rises. Previous topic, what rise, kinetic energy rises? Temperature, right? You rise the thermodynamic temperature, kinetic energy rises. So remember, the kinetic energy proportional to what? Temperature. The kinetic energy is proportional to temperature. Rise the temperature, kinetic energy rises. What is the proof? Oh, we already discussed this in depth one. The kinetic energy of particles found to be what? 3/2 kT, right? So we prove, we derive it, so it's confirmed. Kinetic energy of the particle is proportional to the thermodynamic temperature, 3/2 kT. Okay, now the potential energy proportional to what? Potential energy is proportional to the spacing. Okay. Indirect relation, spacing. Okay. The direct one, what I can see, the potential energy is actually inversely proportional to the intermolecular force. Intermolecular force, but it's proportional to spacing, I can say. Intermolecular force get weaker, potential energy get stronger. But when normally, when the intermolecular force get weaker, what happened to the spacing between the atoms? It will increase, right? Okay, solid, liquid, gas, the bond get weaker, the particle get further one. Okay, so when the intermolecular force get weaker, spacing increases. Okay, so potential energy is proportional to spacing. The atom spacing rises, potential energy rises. Rises. Okay, but the potential energy proportional to spacing works for all the substance. Works for all the substance. Any substance, copper, aluminium, gold. When you melt it, the atom of the gold will get further, and you vaporize the gold. Very difficult to do that. Very high temperature. So the spacing increases further. For all substance, in solid, liquid, gas, spacing rises, except one substance. There is one substance. Never follow. When phase change, sometimes the spacing decrease. What substance is that? Anybody? Normally solid become liquid, spacing a little rises. Liquid to gas, even further critical. But there is one substance. Solid change to liquid, the spacing decreases. What substance? All of you taking chemistry, right? Learning chemistry. A very common substance. You always exposed. Anybody? Solid change to liquid, spacing decreases. Only one substance. What is that? Water. Very good. Water. Yeah. H2O. So water. Water, solid, ice change to liquid. What happened to the spacing? Spacing decreases, right? I don't know the reason. The reason is what? Hydrogen bond, right? Because of the hydrogen bond, decrease the spacing. Okay. So you put the ice cube on the water, ice less dense than the water. So water is, the particles are more closer. So only for the case of water, the potential energy proportional to spacing doesn't work. Okay, only for water. Only for water, the potential energy proportional to spacing doesn't work. Okay, so please put a point. Potential energy inversely proportional to intermolecular force works for all the substances. Okay, so the best idea for you to interpret whether potential goes up or goes down, the correct method is checking the intermolecular force. Okay, spacing 99.9% okay, except water. Okay, yeah. So check when a substance is it EK rising or EP rising. Okay, any one of them rising, internal energy rising. Okay. Okay, so we go back to the slide. Yeah. So okay, so I think I told you this just now. Explained, right? So the internal energy, an increase in EK, internal energy increases. It depends to the temperature. Temperature, please include the word absolute temperature or thermodynamic temperature. Okay. If the examiner, Cambridge examiner, strict, then he wants the term thermodynamic temperature or absolute temperature. So EP manifests as a change in phase. Yeah. So kinetic depends on the absolute temperature. Potential energy depends on the separation of the molecules. Okay. Greater the separation, greater the potential energy. Exceptional case is water. And another highlight, potential energy for ideal gas is 0. Okay. The substance which has the highest potential energy is the ideal gas. Okay. 0 potential energy. Okay. So can we say internal energy proportional to temperature? Can we conclude this? Yes, only for ideal gas. Only for ideal gas. Ideal gas, the U for ideal gas is just sum of EK only. This also will be tested a lot. You know, internal energy sum of EK plus EP. But for ideal gas, no EP1. So for ideal gas, internal energy solely depend to the kinetic energy dash. So for ideal gas, the internal energy is directly proportional to temperature, thermodynamic temperature. Only ideal gas. Yeah. Okay, so you got the idea. Okay. Okay. Now, if you understand quite well your internal energy, then you would understand this law. Okay. This called first law of thermodynamics. Okay. If an engineer want to build an engine and he want to improve the efficiency of the engine, the engineer, let's say you want to do a mechanical engineering, I think you take like a 6 months course doing thermodynamics. Okay. The law of thermodynamics, 6 months course. You are doing this in 1 hour. Okay, a short one. Okay, but go to engineering later, like 6 months course. So how? Of course, engine compartment, the piston moving up and down. You want to improve the efficiency, means the fuel must burn efficiently, and all the energy, the burning energy, must be converted to kinetic. Okay, not as heat. Okay, but nowadays, what is the efficiency of our car engine, our combustion car engine now? Less than 50%. Okay, less than 50%. So 50% convert to heat. Okay, only 50% change to kinetic. Okay, so engineers need to know this law well, so that how to channel all the burning energy into kinetic. Okay, so thermodynamic one. Heat change to that affect the dynamic of the fluid. Okay, so scientists found there are 2 laws governs the thermodynamic. In your syllabus, you only learn first law, only first law. Second law, you never learn. Okay, the first law, according to the scientists, they said it's linked to internal energy law. They say states that the change in internal energy of a closed system must be not exposed to the atmosphere. The engine is a closed system one. The compartment is a closed system, not exposed to the air outside. Okay, it just burn inside, so it's a closed system. So this only works for closed system. The first law of thermodynamics say that the internal energy of a closed system is equal to the heat enters a system and work done on the system. Okay, 1 minute for you to digest what try to the law tried to say. So the simple formula is at the bottom. The changes in internal energy of a closed system is depend to the heat supplied to the system and work done on the system. Okay. Okay, what is the meaning of this? What is meant by rising internal energy? Our focus here, after this, we only focus to ideal gas. Only focus to ideal gas. Okay. Perfect. What do you call model ideal gas. So, how do you rise internal energy of an ideal gas? How do you rise the internal energy of an ideal gas? What is internal energy first of all? Sum of kinetic plus potential. How do you rise internal energy of ideal gas means? How do you rise the kinetic energy of the gas particle? How do you rise it? By rising the temperature, right? So, in other words, layman word, changing internal energy in terms of changing internal energy, I can tell you, how do you heat up a gas? How do you make a gas get hot? Let's say you have a gas in a compartment. How do you make the gas get hotter? What do you do? Heat it, of course, right? You supply heat energy. That's Q. You want to rise the heat. Changes of U is actually increasing the temperature. How do you increase the temperature of the gas? First Q, apply Q, heat it. Okay, heat it, temperature rise. That's one way. Or can say N, you do work on the gas. Do you have realized when you do work on the gas get hotter? Bicycle pump, new generation, never use bicycle pump. Okay. So since you don't feel it, I think bicycle pump is best. Do you have bicycle pump at home? No bicycle. Okay. So when the bicycle pump at the bottom got air, okay, you have to press it so that you compress the air. Okay. When you compress the air quite frequently, you go and touch at the bottom, pump become hot. Okay. So when the gas become hot, how to make gas become hot? You compress the gas. Compress the gas become hot. Okay. So when you compress the gas, you done work on the gas. You do work on the gas. Okay. How you do work on the gas? Either you compressing it or you expand it. Okay. But when the gas become hot, when you compress it, you compress, you do work on the gas. Okay. You of course very difficult, right? When you compress it, use your own energy, you do work, okay, force and distance travel. All the energy you used going to become internal energy of the gas. Okay, become hot. Okay. So how do you make the gas become hot? Two ways: by supplying heat and to do work on the gas. Okay, compressing it. When the gas expand, what happened to the gas? Become cold or hot? The gas expand. Become cold. Become cold. Okay, or perfume maybe. Okay, when you spray up, the liquid inside is actually form of gas. When it comes out, like turn to become gas, expand. So you go and touch it, it's cold. It's cold. Gas expand, cold, and compressed, hot. Okay. So that's the first law. Very easy law based on conservation of energy. Okay. You want to rise the internal energy. The technical term is not heating the gas. You want to rise the internal energy of the gas is two ways: by heat the gas, heat enters the system, okay, and the work done on the system. Okay, work is done on the system. Okay. Okay. So let's see how well you get the idea. Okay, let's see. You have a closed system. Okay, piston. Okay, there is a piston. There is a. Okay, you heat the gas. You apply a heat energy of 20 joules. Okay, you heat the gas. Okay, you heat the gas. Okay, okay. At the same time, the piston moves upwards. The piston moves upwards. Okay. Work done is 5 joule. Yeah. You heat the gas, 20 joule. The piston move upward. Work done is 5 joule. Okay. How much is the rise in internal energy of the gas? So, what is the law? First law of thermodynamics. The changes in internal energy is the heat supplied to the system plus work done on the system. That's the law. Okay. So, the heat supplied is you heated 20 joule. You say positive 20 joule. You heated it. So, heated is a positive effect to the internal energy. So, positive 20. Okay. Work, is it positive 5 or negative 5? Positive 5. Is it positive 5 or negative 5? When gas expand, you're going to make the gas cooler or hotter? Make the gas cooler, right? Okay, when expand. So the work done during expansion, when the gas expand, the work is negative 5 joule. Work is 5 joule because it's expanding. It gives a negative effect to the internal energy. Internal energy reduces actually, okay, when I expand. So the gain in internal energy of the system is just positive 15 joule based on first law of thermodynamics. Okay. The system gain internal energy of 15 joule. So conclusion is the gas get hotter. Okay, it should get hot. Okay, yeah. So something new you learn here. Remember, the W is considered positive when compressed. When compressed, the gas is compressed. Okay, compressed positive. When expand, negative. Okay. The Q is positive when heated. Okay. Q is negative when you cooling the system. When do the cooling. When you freeze it or cooling, and then the Q is negative. Negative means negative effect to the internal energy. Yeah. Actually, this law is also can analog to human body. Okay, if you want to remember. Like your internal energy is the amount of fat you have in your body. The amount of fat, the amount of energy you stored in your body. So the amount of fat in your body is depend to the amount of food. Q is food lah. how much of energy you taking from the food. You take more food, most probably more chances you get more fat, right? More internal energy stored. Okay, but the internal energy store also depend to the how much of work you do, right? Okay, you eat food 10 joule, but at the same time you do work of 10 joule, internal energy fat 0, right? Never rises. Okay, so this works for the human body too. Internal energy. Same thing happens for the gas. Okay, gas also work like a human mechanism. The gas receiving energy and no work has been done. What the gas will do is store it as the internal energy. Okay, when it store as internal energy, what is the consequence? Gas become hot. Okay, the gas become hot. Okay, yeah. So we get the first law. Any questions? Okay. Okay, I think I already explained this to you, right? So changes of U equals to Q plus W. The Q is positive when heat is transferred to the system, when heated. Okay. Q is negative when heat is transferred from the system. When you cooling, when you freeze, put in the freezer, heat has been removed from the system. So Q is negative. Okay. Work positive when work done on the system. So what I said, work done on the system is when you compress. When you compress, it's work done on the system. When the gas is expand, Work done on the system is negative. Work is done by the system. When a gas expands, gas does work. Okay? Gas forcing itself to do work when it expands. Okay? When it compress, you do work on the system. Okay? Yes, so yeah, hope you got the idea. First law of thermodynamics. Okay, now the work, right? The work, okay, the work has one formula for you to remember for gas. What is work formula? You learn in AS. I think indirectly I told you in AS. Work. What is the work formula actually? The basic formula is force times distance travel, right? Force times distance travel. For the gas, force is what? It's a pressure times the cross-sectional area times the distance travel. Okay. The area times the distance travel is actually changes in volume. So this work. Okay. Or you go to more scientific term, we can write work is the integration of PdV. In terms of integration, PdV. P is what? Pressure. dV is what? Change in volume. Okay. So if I plot pressure versus volume, okay, you know Boyle's law, right? Boyle's law, gas, the graph going down, right, like this. Okay. So let's say from the volume of V1, it go to volume of V2. How much is work done to move from V1 to V2? Actually, integration is what? Your linear, your advanced knowledge. Integration is what? Area under the graph, right? PdV. So actually, the area under graph of P versus V, this is your work done. Please include this. Something little elaboration about work. Work for gas formula is P changes in volume. Okay. But don't define work as P changes in volume. What is the definition of work? So force times distance travel to the direction of the force. That's the definition. But for the gas, you can derive this. P changes in volume for a gas. In other words, if they give pressure versus volume graph, the area under graph is your work done. Okay, P changes in volume. Sometimes in exam they'll trick you. Instead of PV, they put V versus P. They put V versus P, then the area is on your y-axis. Okay. Yeah, so not much to say. Okay, so let's go to the whiteboard. I need to tell something. Okay, so just now we saw the system. Okay, a piston was heated and the piston moved up, and we use this example. The piston moved up, and work to expand, the work done is 5 joule. Okay, the heat supplied is 20 joule. Okay, so let's say this is the one. This is the model of engine, right? Engine 4-cylinder. I got 4 pistons, right? Or 6, depending on how big is the engine. So each engine, when the fuel pour into the in the cylinder, what happened? Of course, the ignition happened. The spark plug will explode the fuel, so piston will move down. Okay, so the fuel gives Q, 20 joule. Okay, and the piston moves up and down. Does work, turns the wheel. Okay, my question now, can you tell if this is what happens to this cylinder? Okay, Q is 20, work is 5. Yeah, Q is 20, work done is 5. What is the efficiency of this cylinder? If this is an engine, what is the efficiency of this engine? How many percent? What is the efficiency? Q is 20, work is 5, internal energy rise by 15. What is the efficiency of this? If this is part of an engine, what is the efficiency of this engine? How many percent? 1 minute for you to think. Come on. How many percent? Q was 20. Work done is 5 joule. Rise in internal energy is 15 joule. What is efficiency you learn? Useful energy output, we go for energy lah. Useful energy output over the input, right? Okay. So decide what is the input, what is the output, and what is the efficiency. How many percent is the efficiency? What is the input? What is the input in this system? The Q, the changes of U, or the work? What's the input? What do you input into the? Is the fuel, right? Okay. What is the input here? The input is the Q, right? Q is the input, 20 joule. Okay. Which one is the output? You want that energy to become what? You want the energy to become what? You want it to turn to become U, or you want the energy to become work? You as a owner of the car, you want the engine, whatever petrol poured into that, the energy, the Q of that fuel, you want to convert to what? Internal energy or the work done, which is useful. Because you want it to do work, right? You want the wheel to move, okay? So we don't care about the internal energy. We want it to do work, okay? Whatever fuel you pour, we want it to convert to work, okay? So then, what's the efficiency of this system? The useful output energy is actually what? It's the work. So 5 joule divided by input is 20, so times 100%, so it's 25%. So the efficiency of this engine is 25%. Okay, so 25%. So you as a consumer, do we like the internal energy of the gas to rise? Do we want the internal energy of the gas to rise? No. Okay, we don't want the internal energy of the gas to rise. We want the gas, whatever heat supplied to the gas, we want the gas to decide to convert most of them to work. Okay, we want them to become gain less internal energy. Okay, that's the technology now trying to do. You know, the VTEC, DVTI, all type of technology. Try to play around with this formula. This is the law. We can't alter it. But they are trying to use the technology so that make the gas, the type of gas they use, make the fuel they use. They make sure that they try to make sure that, not to say make sure, they are trying their level best so that majority of the energy convert to what? Work. Okay. So tell me, if the change in internal energy is 0, then what happened to the efficiency of the engine? If the change in internal energy is 0, what happened to the efficiency of the engine? Become 100%, right? 100% efficient. Okay. So if you have a car engine with 100% efficient, do you need a radiator to cool down the engine? Do you need a radiator to cool down the engine? No, because the temperature of the gas won't rise because internal energy never rises. Okay. So try to understand what is meant by changes of U, Q, and the work done. Okay. So changes of U, we thought maybe it's good for gas, it stores energy, but as a consumer, it's bad for us. Okay, we don't want the gas to become hot. Okay, what is the purpose? It stores energy inside, never release it. Okay, yeah. So that's some ideas about the first law. Any questions? Questions? Yeah, every time I have to do this. Okay, so one example. Okay, what I told you. Look at the question, look at the solution. Does it make sense for you? A fixed mass of an ideal gas absorbs. The word absorbs, release, be careful. The gas absorbs 2000 joule of heat. the gas absorbs 2000 joule of heat. So Q is positive or negative? The gas absorbs. That means heat has been supplied to the system. So 2000 is actually, the Q is actually positive. So positive Q. Positive means positive in terms of internal energy. There is a chance for the internal energy to rise, right? If it's a positive effect to internal energy, then the Q is positive. Heated. So 2000 joule of heat and does 500 joule of work in expansion. So work is positive or negative? Work is negative, right? It's negative 500 joule, right? It should be negative. Okay, expansion one. And gas expand, it's not a positive effect for internal energy. Okay, like for example, when you do work, it's a negative effect for your fat, for your internal, your stored energy. Yeah. So expand work is negative lah. So how much does the volume change? Okay, so they're asking for the volume change. The pressure was 20 kilopascal. How much does the volume change? So this is the work formula. P changes in volume should be 500. So we find the changes in volume 0.025. Okay. This formula, the P changes in volume. The P we make constant. This only works when the gas pressure P versus V graph looks like what? Like constant pressure. Okay. Like constant pressure. The pressure is constant. V1. If the graph is a flat line, then yeah, the area of the graph is like P times the P, the vertical height P by P times the changes in volume. Okay, so P changes in volume is the work. But here you are quite unfortunate. Sometimes they can give a curve. Okay, normally curve is very practical. Boyle's law, curve. When they give curve, then again work still need to find the area, so you have to count the number of boxes. Okay, like how you do in biology, right? Count number of boxes to find the area. Okay. Okay, but if they say normally the question will be with constant pressure, normally it will be constant pressure. So P changes in volume, pressure is constant. So that's a 0.025. I hope you understand the A. P changes in volume is the work done. Okay, next, what is the change in internal energy of the gas? So how much is the change in internal energy? So you have to go for first law of thermodynamics. Okay, the change in internal energy is heat supplied to the system and work done on the system. Okay, so Q was 2000, W is negative 500, so internal energy should write by 1500. Okay, so one warm-up question for first law of thermodynamics. Okay. Okay. So before we go to this, I don't want to go to this yet. Okay. Before we go to this, we go to the Word document. Okay. The day we did this, right? First law of thermodynamics. So here, this you need to fill up your information. Okay. First thing we learn about internal energy. What is internal energy? Write down. What is internal energy? Internal energy of substance is the sum of kinetic energy and potential energy possessed by all the particles in the substance due to random motion. Okay, as a supporting fact, write the formula. What is the formula? U equals to what? U equals to sum of EK plus sum of EP. So it's the PowerPoint, right? So write it down here. Okay. So what is internal energy of a substance? Total internal energy of substance is the sum of kinetic energy and potential energy possessed by all the particles marked due to random motion. Okay, due to random motion. Okay, next two. What's the answer? Kinetic energy of the material is dependent on what? Thermodynamic temperature or absolute temperature, right? Depend to thermodynamic temperature, absolute temperature. Okay, so this all are the same idea I told you. So first law of thermodynamic, what is internal energy? Write the formula, changes of EK plus changes of EP. And in this small bracket, what is work done formula? Work done is P changes in volume. Okay. So, but Cambridge happy to see this integration of PdV. This covers everything, right? Whether it's a flat line or a curve, integration of PdV covers everything. But Cambridge still give you mark when you say P changes of volume. They expect you to write P changes of volume, but they'll be happy to see you do integration of PdV. Okay, so first law, then as I told you, when W positive, when W negative. Okay, so there is something last about 1 minute. Just I finish this. The W, Q, and changes of U sometimes they become zero. They become zero. Okay, and the question what they tell, then you conclude that the work zero. When the work becomes zero. When work becomes zero. When what becomes zero, work becomes zero. Anybody? When the work done becomes zero. When the changes in volume is zero. Okay. When the question said no changes in volume, so work is zero. Okay. When Q zero, sometimes Q will be zero. Okay, indirect question lah. They won't tell you Q, but indirectly they said tell you Q is zero. When they said Q is zero, when they said free, okay, that's I put here. When they say free expansion or free compression, when they say free means no energy was get into the system. So Q zero. And they said free what? Free expansion or compression lah. Then Q is zero. When changes of U zero? When what becomes zero? As I said, your syllabus most of the time this is for ideal gas. I'm asking for ideal gas. For the ideal gas. When changes U for the ideal gas zero? When one becomes zero? When what becomes zero? Changes of U zero. Anybody? Changes in the temperature. Changes in temperature zero. No change in temperature means no change in internal energy. Okay. Okay, so this is the last thing I want to tell you today. So remember these three. Work zero when changes of volume zero, Q zero when free expansion or compression, changes to U zero when no changes in temperature for ideal gas. Yeah. Well, so I stop here. Maybe the next class we continue with this tomorrow. Okay. And this week, tomorrow we need to do the just 1 minute. Show you which paper to do for discussion for tomorrow. Okay, I think that day we did what? We did Gen 18. I think still some questions left for me to discuss. I'll go back to that paper. Which paper I told you to do? Okay, I select one. July 17. We haven't done this yet. Yeah, correct. Okay, we haven't done this yet. Have we done this? We done last class. Oh, July 17. Okay. So we done July 17. So we go the above one. We go to paper 1 Gen 17. Okay, for tomorrow. Okay, paper 1 Gen 17. So please do. And I'll still go back to paper 1 July 17 first. Some questions still left. Okay, thanks.